Alright, so in this chapter we are going to talk about momentum. Momentum is defined as the product of the mass and the velocity of a particle. And momentum is clearly a vector because velocity is a vector, mass is a scalar, and the product of a scalar and a vector is always a vector. The symbol for momentum happens to be P. Okay, the unit of momentum is kg meters per second. There is no particular name for this combination of units, it's just called kg meters per second. Alright, so that's the definition of momentum. Interestingly, Newton's second law can be written in terms of momentum. So let's see how we would do that. So Newton's second law, as you remember from an earlier chapter, is net force equals mass times acceleration. Now you know that acceleration can be written as the derivative of the velocity, as you've seen in chapter 3. Now, if the mass is constant, there is no harm in moving it into the derivative. So you know that the rules of derivatives say that if you have a constant quantity multiplying your function, then you can feel free to pull that constant out of the derivative. So here we are putting it back inside the derivative. So this is what we have. F net equals d dt of mv, but we just saw that mv is the momentum. So F net is equal to d dt, or the derivative of the momentum. And so this is Newton's second law. Now you might say that what's the point of doing this? Like, what was wrong with F net equals mass times acceleration? Well, the advantage of doing this is that there might be systems where the mass is not constant. So in all the examples that you've seen in earlier chapters, the mass of an object has always been constant. But you can easily think of examples where the mass of an object is not constant. Can you think of one yourself? Here is one example, a rocket, for instance. When a rocket is flying in space, or anytime the rocket is moving, it gives off exhaust. It shoots off exhaust. So as it's shooting off the exhaust, it's losing a lot of mass. So the mass of the rocket is not constant. So in problems like this where the mass is not constant, you can still apply Newton's second law in the form F net is equal to dp dt. And incidentally, this is the form in which Newton himself presented his second law. F net equals ma is a sort of simplified version of that for cases where the mass is constant. Now, fortunately for you, we will not be going into problems like this, like the rocket problem where the mass is not constant, because those problems are usually pretty hard. But I'm just mentioning this so you understand that this form of Newton's second law is more general than F net equals mass times acceleration. All right, now let's define a new concept. So we'll keep coming back to momentum, but let's just learn about a new concept now. And that is the concept of impulse. So the impulse of a force which acts from a time t0 to t is defined like this. Okay, so the impulse is just the integral of the time integral of the force over the period of time that it acts. Right? What's an example of this? So consider a ball which hits a bat, right? So suppose you or a wall or something. So you have this ball that's coming in, and it hits the wall. So what are the forces that what kind of forces act on it when it hits the wall? So a very large force acts on it for sure, and that would make it turn around and bounce back. Is that force a constant force? The answer is no, because when the ball hits the wall, just as it's making contact, the force is small, but then as the ball sort of slams into the wall and squeezes against the wall like this maybe, then the force might be quite large. Then the ball just takes off in the opposite direction, and as it's taking off, the force from the wall would decrease, and then becomes 0 when the ball loses contact with the wall, right? So if you wanted to make a graph of this force, if you wanted to make a graph of the force as a function of time against the time that it acts, so the force only starts acting when the ball first makes contact with the wall, and at that time the force is small. But then as the ball squashes against the wall, the force might increase tremendously. And then the ball starts rebounding and going back, and as it begins to take off, the force will decrease, and eventually the ball, at some point, the ball just completely loses contact with the wall and flies off. And at that time, the force becomes 0. So the force would have this kind of time dependence. And the time interval over which the force acted, let's just call that delta t. This is our time axis, and we'll call this time interval as delta t. This is very, very small. So the ball only remains in contact. We are talking about a tennis ball bouncing off of a wall. So the ball only remains in contact with the wall for maybe a few milliseconds or something like that. So it's a very, very small time interval over which the force acts. So what is impulse? Impulse, the symbol for impulse is J, and as you can see in this chapter, all the symbols are completely off. Symbols and their letters are completely off. Momentum was P, impulse is J. So J is defined as the integral of the force over the time interval that it acts. So if the force acts from t equals 0 to t equals delta t or something like that, so I should probably erase the delta t from over here, then this will just be 0 to delta t. I think in the PowerPoint I say t initial to t final, which really means the same thing. Maybe I'll just do that. T initial to t final, just to make it match with the PowerPoint. The point is that the integral should only make sense as long as the force is not 0, and the force is not 0 between t initial and t final. So that is the formal definition of impulse. Okay. Now, normally we don't have to actually evaluate this integral. Like if the force is given to you as a function of time, then you can just go ahead and evaluate this integral and find the impulse. But we don't normally have to do this integral, because we are generally satisfied by replacing this variable force by a constant force. So let's just pretend that the force that the wall exerts on the ball is a constant force. So we would just call that F average. So we are replacing the actual force with this constant force. So what is the impulse of this constant force going to be? So if the force is constant, so it's easier to replace the actual force by a fictitious constant average force. And what is the impulse for this average force going to be? The good thing is that it's a constant force, so the impulse would just be F average dt, t initial to t final. If F average is a constant, so you can just pull it out of the integration. T dt, t initial to t final. This is a very easy integral to do. Integral dt is just t. So it's going to be F average times t minus t initial. We are just going to call t minus t initial as delta t. So it's F average times delta t. And that is our impulse. So to summarize, if you work with and the impulse is a vector, so strictly speaking, there should be vector signs over all of these. So to summarize, if you work with the actual force, the impulse is simply the integral of the force dt over the time interval that the force acts. You can also write the impulse as f average times delta t, where f average is a fictitious average force that you're using instead of the real force, which has a very complicated time dependence. So f average is a fictitious average force which you're using. And in terms of that, the impulse is simply the average force multiplied by delta t. Now, for all, usually we are happy with just this average force. We don't really care about the details of the actual force that's acting, just because the force is acting for such a short amount of time. So we're just happy with pretending that the force is constant and just working with this constant average force, right? Okay, so that is the definition of impulse. So impulse is one of these two, either this one or this one, depending on which form of the force you want to work with. Now, how is impulse related to momentum? So we first learned about momentum, now we are learning about impulse. Is there any connection between them? Absolutely. That crucial connection is called the impulse momentum theorem, and that's what we're going to talk about next. So let's write down the formula for the impulse, J, and let's just write down the rigorous formula, f of t dt, t initial to t final, right? Now let's put in Newton's second law. So Newton's second law, as you know, is F net equals dp dt. If the only force acting on a particle is just F, then F net and F are the same thing. So I can just write this as T0 to T dp dt dt. That is J. So P is the momentum of the particle, and the force, the net force acting on the particle, F net, is equal to dp dt. That's Newton's second law, right? So that's all that we did over here. Now, you know that whenever you have a dp dt, that's a derivative, and if you integrate a derivative, you just get back the original function, right? Because you know that differentiation and integration are opposite operations. So if you do dp dt, that means you're taking the derivative, but then if you integrate the derivative, you get back the original function. So this is nothing but p, the original function, evaluated at the two endpoints, t0 and t, right? I hope it's clear what we just did. This is the derivative, dp dt is the derivative, and when you integrate a derivative, you just get back the original function, right? So if you have a function y of x, if you differentiate that, that's dy dx or y prime x, and then if you integrate y prime x, you just get back y, right? So that's exactly what we did. So p evaluated at t times t initial and t final. So that is just p final minus p initial, and that is the impulse J. So p final minus p initial is just the change in momentum. The definition of delta, which is change, is just p final minus initial. So you get this very important relation that J, the impulse, is equal to the change of momentum, and that is the connection between impulse and momentum. Impulse is equal to the change of momentum. All right, so that's the impulse momentum theorem. Let's look at a quick illustration of the impulse momentum theorem. Let's take a look at this problem, and please try this problem. Pause the video and try this problem yourself, and then we will then look at how I work it out. So this is slide 4. It's saying that 100 Newton force acts on a bullet in the barrel of a gun. So here is the barrel of the gun. Okay. And the bullet is somewhere at the back over here. So what happens inside a gun? You have an explosion, right? And that causes rapidly expanding gases. And those gases exert a force on the bullet and exert a tremendous amount of force on the bullet. That force acts on the bullet while it's still in the barrel of the gun. And then the bullet emerges from the, what's this thing called, from the opening here with a very high velocity, right? So that's how a gun works. So what the problem is saying that while the bullet is inside the barrel of the gun, it's feeling this 100 Newton force, and you're given the mass of the bullet, and you're also told how long it stays inside the barrel of the gun, right? So let's try the first part. Calculate the acceleration of the bullet. So to find the acceleration of the bullet, you can just use Newton's second law. So the force, there's only one force acting on the bullet. We are going to ignore friction and all that. So there's only one force acting on the bullet. That's the 100 Newtons, right? So applying Newton's second law, since we are ignoring friction, so net force would just be F. So applying Newton's second law, you get F equals ma, or A is equal to F divided by m. So 100 Newtons divided by the mass of the bullet, which is 0.01 kgs. So this is going to be 100 newtons divided by kgs. So newtons is kg meters per second square, as you remember from chapter 5. And if you divide that by kgs, then the kg cancels out and you get 100 actually this is 10,000. I shouldn't have this comma here. Meters per second square. So that's the acceleration of the bullet. So very high acceleration. Okay. So the question is, what is the okay? So that's the first part, right? Okay. So there was nothing new here. It's just application of Newton's second law. Calculate the bullet's final velocity. So the final velocity of the bullet as it emerges from the gun, that is something you can calculate just using kinematics. So you know the initial velocity of the bullet, which was 0. You know the acceleration, you know the time. So you can use this equation v final equals v initial plus acceleration multiplied by time. So v final is what we are looking for. V initial is 0, acceleration is 100, 10,000 multiplied by the time, which is 0.5 seconds. And so this is meters per second squared, and this is seconds, so the answer is going to be in seconds. So this is going to be 5,000 meters per second. Okay. 5,000 meters per second. So, all right, so this parts A and B are just a review of stuff that's happened in previous chapters. So there is nothing new so far. Let's calculate the bullet's change in momentum. So the change in momentum delta P is always P final minus P initial. I should just stick with my notation here. I always use no subscript for final and 0 subscript for initial. The initial momentum was 0. What about the final momentum? The final momentum is mass of the bullet, which is 0.01 kgs, multiplied by the velocity of the bullet, which is 5,000 meters per second. And so that's just going to be 50 kg meters per second. So that is the change in momentum, right? Now let's calculate the impulse experienced by the bullet. The impulse is going to be force multiplied by the time that the force acts for, right? in this case the force is constant. So yeah, so the impulse, excuse me, the impulse is the integral of the force. But if the force is constant, it just becomes force multiplied by delta t, as we've seen over here. So if the force is constant, or if we can pretend that the force is constant, then the impulse is just force multiplied by the time over which it acts, right? So in this case, the force is given to be constant. So it's just going to be 100 newtons multiplied by the time that the force acts for, which is 0.5 seconds. So this is going to be 50 Newton seconds. And you can easily convince yourself that Newton seconds is the same thing as kg meters per second, because newtons is kg meters per second square. If you multiply that by seconds, then one of these cancels out. So it's kg meters per second. And so this just shows you that the impulse momentum theorem is true. You get the same answer. So this just shows you that J is the same thing as delta P. All right, so just a quick demonstration of the impulse momentum theorem. Okay, now there are many consequences. There are many consequences of this one equation that we just derived. Let me go back to that equation. So the impulse is given by F average times delta t, right? And we are just going to stick with this form for now, because for practical situations, we are usually just interested in the average force that acts. And that is equal to the change in momentum delta p. So F average delta t is equal to P final minus P initial. There are many practical applications of this equation. Let's look at some of these applications. So in one class of applications, the change in momentum is fixed, right? But the F average and delta t might not be fixed. They might be things that you can control, but the change in momentum might be something that you cannot control. And I'm being a bit sloppy here. I should just put these vector signs up here. Okay, all right. All right, now let's look at a situation where the change in momentum is fixed. So suppose you are driving this car, not you, some unfortunate person is driving this car, and they are driving at 70 miles per hour, something like that. And then all of a sudden they find that the road has ended, and in front of them they can choose to collide with two different things. Like they can decide which one they want to collide with. So there is a brick wall, and there is a mountain of hay, a huge mountain of hay. Now, if you were driving this car, which one would you choose to collide with? Right? The answer is you would obviously choose to collide with the mountain of hay, right? You would not want to collide with this. Why is that? Why is it a good idea to collide with the mountain of hay? Let's think of this. Let's try to understand this in terms of the equation that we just derived, right? Okay, the car has a certain momentum. It has a mass, it has a velocity, high velocity. So it has a certain momentum, right? Its initial momentum is mv. What is its final momentum when it comes to a stop? Its final momentum is going to be 0, right? So its change in momentum, its delta p, is just going to be final momentum, which is 0, minus its initial momentum, which is mv. So delta p is just going to be m times v, minus m times v, and there is nothing that you can do. That is true regardless of how the car comes to a stop. So this is going to be the same regardless of how the car stops, either by colliding with the brick wall or by colliding with the mountain of hay, right? So the change of momentum is the same. However, the average force felt by the driver or felt by the entire car would be different in the two cases, right? And why? That is because the time of collision is going to be tremendously different in these two cases. So if the car collides with the brick wall, what is delta t going to be? The car will come to a stop very, very abruptly, and so delta t would be very small. So brick wall, delta t would be very small. So our equation is F average times delta t is equal to delta p. Delta p is fixed. If delta t is small, then F average has to be large. When two numbers multiply to a fixed number, if you make one of them small, the other one has to increase in order to multiply to the same thing, right? So if the delta t is very small, then the F average would be very large. And so if the car comes to an abrupt stop, then the average force felt by the car is going to be tremendously large, right? And so that's going to cause a lot of damage to the car and to anybody inside the car. However, if delta t is large, right? So that's for the brick wall, and for the hay, delta t is going to be large, right? Because the car will take a longer time to stop. And so F average will be less because their product is fixed. And so colliding with the hay is a good option because in that case, the average force of the collision is going to be much smaller, right? So that is one illustration of this equation. There are many other similar examples. I'm sure you can think of many yourself. One example that I mentioned in class is that suppose you go bungee jumping, right? And just as you're about to jump off the mountain, the bungee company tells you that we are a bit short of cash right now, and so we haven't been able to buy these expensive bungee cords. So instead of bungee cord, today we are going to use a metal chain as you're jumping off. So you will probably not go with them at that point, right? Because you don't want to jump off a mountain with your legs, with your feet tied to one end of a metal chain. Why? Because the metal chain will bring you to a stop very abruptly. The chain is not extensible at all. It's very strong and it's not extensible. And so the moment the chain is taut, it will bring you to a stop. And the delta t will be very small. F average would be very large because your delta p is fixed in that case, right? However, if you use a proper bungee cord, that is quite extensible. So the bungee cord will stretch and bring you to a much gentler stop over a longer period of time. So with the bungee cord, your delta t is going to be much larger and your F average is going to be much smaller, right? So that's another example of that. There are many other examples too. The whole purpose of the the automobile, I can't remember what that thing is called. Airbag. Okay, yeah. I was thinking air bubble. Okay, it's not an air bubble. Anyway, so the automobile airbag does the same thing. So if the car comes to an abrupt stop, then as a result of inertia, the driver would continue moving at the same speed of the car and slam into the steering wheel of the car, and the steering wheel would bring them to a stop immediately, which would mean a very small delta t and a very large F average. On the other hand, if the airbag can inflate just in time, then the airbag acts like a cushion, and the unfortunate driver would come to stop a little bit slower. So the delta t is increased a little bit, and the F average is lowered. Right? So there are many similar examples. Okay. So we talked about airbags. Now, there is another class of examples of applications of this equation. So let's write down the equation again. F average times delta t is equal to delta p. Now, you might have certain situations where you can control both the F average and the delta t. And together, by controlling these, you want to manipulate the delta p as much as possible. So this class of examples, delta p is something that you can control. Because you can control both the F average and the delta t. So what's an example of that? One example which I mentioned in class is the example of the golf swing. Now, I know absolutely nothing about sports, and so here I'm just talking about something that I've been told. So it's not something that I have direct experience of. So apparently the way it works in golf is you have this ball sitting on this tee, and then you swing the golf club. So let's say this is the golf club. At this point, it's held in the person's hand, and the person swings the club and brings it to and hits the ball, right? So apparently, what you're supposed to do is you're not supposed to stop your swing the moment you make contact with the ball. Instead, you're supposed to continue your swing, and that's called the follow through. You're supposed to continue your swing as long as you possibly can, and maintain contact with the ball as long as you possibly can. So hopefully you can understand from the equation that we have here why that is a good idea. Because you want to maximize the delta p for the ball. You want it to leave with the highest possible momentum that you can give it, right? So in order to maximize delta p, you want to maximize not just F average, but also delta t. So that is the whole reason for trying to maintain contact with the ball as long as possible. Not just give up contact, not just slow down your swing the moment you make contact, but keep following through your swing and maintain contact as long as you can. And that's going to give the ball a greater momentum as it takes off. So that's one example of that. I can give you one more example. So you know that long-barreled guns like rifles, you've probably figured out that I'm a fantastic artist. Okay, anyway, and here's a short-barreled gun, handgun or something. I know absolutely nothing about guns either. So here is my what should the trigger be like? Okay, so anyway, so this is the trigger probably. So you know that short-barreled guns like handguns, pistols, they are much less lethal than long-barreled guns like rifles, which are absolutely deadly. Why is that? Well, let's assume that the force acting on a bullet in both a rifle and a handgun is the same. That's not quite true. The force acting on the bullet in a rifle is much greater. But for now, let's just assume that the explosion in the gun when you pull the trigger exerts the same force on the bullet in both of these, right? Now, in which case will the force have an opportunity to act on the bullet for a longer time? Clearly, that's the case. Delta t, the time over which the force acts on the bullet, is going to be larger if the barrel is longer, right? And here delta t is going to be smaller. So if the F is the same, if the F average is the same, then F average times delta t would be a larger number for the rifle. And so that would mean that delta p is greater. And here delta p for the bullet is smaller, so the bullet will exit with a smaller momentum or smaller velocity in the case of the handgun, right? This principle was first discovered in America, and at the time, roughly at the time of the Revolutionary War. And it played an important role in Americans winning the Revolutionary War, because apparently the British used muskets which were shorter, which had a much shorter barrel, and so they were not as effective or deadly as rifles, which American soldiers began to use during the Revolutionary War. Okay, all right. So the next slide. So we talked about all this. So I have an example, a numerical example of our equation f average times delta t equals delta p. You can just look at this on your own. Okay, let's try this example. This example is a bit counterintuitive, so I'll let you think about this a little bit and see if you can set it up and solve it yourself. And then we will work it out, sorry. Then we will discuss it, okay. All right, so this is the example on slide 8. So it's saying that a tennis ball and an iron sphere of the same mass are traveling horizontally along a frictionless surface, and they strike a wall. So the question is, then one of them comes to a stop immediately after the collision, which is and that's the iron ball, and the tennis ball rebounds, and you're given the velocity with which it takes off. Which of the balls exerts a greater force on the wall? Okay, now the question is, which of the balls exerts a greater force on the wall? You might at first be stumped, like how can I find out the force exerted on the wall by a ball? But if you think about it and apply Newton's third law, which you learned in chapter 4 and 5, the force that the ball exerts on the barrier is going to be the same as the force that the barrier exerts on the wall, right? Newton's third law, action and reaction. So it's a lot easier to calculate the force exerted on the balls by the barrier. So here's our barrier, and let's say this is one of the balls that's coming in, right? Let the mass of the ball be m, right? And let's say that its initial velocity is v0. Okay, so after it hits the wall, so I'm going to draw that with a different color. It starts heading back, and let's say its velocity is v final. Its mass stays the same, of course. Its velocity, its new velocity is v final after it hits the wall, right? So let's calculate its let's calculate the force that it feels, the average force that it feels. Now we have this equation, f average times delta t equals delta p, right? So f average would be delta p divided by delta t. Delta p is just the change in momentum, and delta t is the time over which that change in momentum happens, which means the time that the force acts. So let's calculate this. And this is all one-dimensional, so I'm not bothering to put the vector signs. Like strictly speaking, I should have had a vector sign on top of the f average and a vector sign on top of the p here, but everything is one-dimensional, so we don't really need the vectors. We can just keep track of directions using plus or minus signs. So let's calculate f average. So f average would be final moment, delta p is final momentum, so final momentum would just be mv minus initial momentum. So initial momentum, what is the initial momentum going to be? Let us be careful with signs. Remember that momentum is a vector. So for a vector quantity, you have to take its sign into account somehow, right? So in this case, we can just adopt a sign convention that right is the positive direction, plus VE just means positive. Uh, that's our sign convention. So any vector which points to the right should be given a positive sign, and any vector that points to the left should be given a negative sign. So mv minus mv0. Notice that I gave the initial momentum a negative sign because it points to the left, right? Final momentum was a positive because it points to the right, divided by delta t. So F average is equal to mv plus v0 divided by delta t. That is the average force. You can apply this formula to either of the balls, right? And calculate the average force on either ball. Now, we are not going to do the whole problem using all the numerical values. I'll let you finish that yourself. But you can see what the answer will be by just looking at this formula, right? One of the balls comes to a stop. So that means V final is 0 for one of the balls, the iron ball, right? So in that case, the F average would just be mv0 divided by t. For the other ball, the V final is not 0. The V final is some 4 meters per second, right? So in that case, the F average would be clearly a larger number because it would be m multiplied by 4 plus 5, 4 plus 5 divided by delta t. So that would be larger. So the ball that rebounds feels a greater force. And by Newton's third law, that means that it exerts a greater force on the wall, which is the same thing as saying that it exerts a greater force on the wall. So this is a counterintuitive result. You might have thought that they both exert the same force because they're coming in with the same mass and same velocity. But whether something rebounds or not determines the force that it exerts. If it rebounds, it's going to exert a greater force. If it doesn't rebound, it's not going to exert much of a force. There's a nice demonstration of this which I sometimes show in class, and I wish I could have shown it to you guys. But since I can't show you the demonstration, I'll just try to draw it over here. So I have this brick, very heavy brick, and I have a pendulum with a pretty heavy iron bob. Okay, so what I do is on one side of the brick I put some putty. Now if I swing the pendulum to one side and let it hit the brick, it does not rebound, because when it hits the putty it just comes to a stop. It does not bounce back, right? And then the brick is not pushed over. The brick just sort of tips over slightly, but it doesn't tips slightly, but it doesn't completely fall. But if I turn the brick around so that now the putty is on the other side and the pendulum is allowed to hit the brick with no putty, so in that case what happens is that the pendulum bounces back after it hits the brick, right? It rebounds and the brick completely topples over and falls, right? So this shows very clearly that if there is a rebound, if an object rebounds, it exerts a greater force, whereas if it does not rebound, if it just comes to a stop after the collision, then it exerts a much smaller force. And there is a nice practical application of this. You know how hydroelectric power plants work. So you have I'll probably draw it here. You have a mountain and then you have a waterfall with water falling like this. And so what happens in a hydroelectric power plant is that you have a turbine which with these paddles, uh, and so the water turns the paddles and makes the turbine rotate, and the rotational energy of the turbine is converted to electrical energy. You're going to learn how to do that in physics too. So the rotational kinetic energy of the paddle is of the turbine is converted into electrical energy. Now you want to make sure that you want to design the paddle in such a way that it gets most of the kinetic energy. It extracts as much kinetic energy as it can from the water, right? So having straight paddles like this is not a good idea. The better way to do it is to use paddles which have this kind of a shape. Why is this kind of a shape good? Because if water falls on the paddle like this, if you have a jet of water falling on the paddle like this, the water will rebound if there's a shape, if it's shaped like that. So if my diagram is completely atrocious now. So here, let me just draw one more. So if the paddle is curved like this, then the water hitting the paddle rebounds, right? Whereas if the paddle is just straight, then the water doesn't rebound that much. But if the paddle is curved, then the water rebounds, and so it delivers a much greater blow to the paddle and makes the turbine spin faster. Okay, this is called the Pelton wheel. So it's just an illustration of a practical application of what we are learning. All right, now we're going to talk about one more thing, and then I'll end this video. So the next thing that we'll talk about is applying Newton's second law to a system of particles, and that would lead to conservation of momentum. Okay. So we're going to apply Newton's second law to a system of particles. Okay, let's take the simplest system of particles in the world. A system of particles just means a large collection of particles which might or might not be exerting forces on each other. Let's take a very, very simple system of particles which consists of just two particles, right? So our system is the simplest it can be. It consists of two particles, and let's just say that they exert some forces on each other. So just imagine that they're connected by this invisible spring, a very, very light invisible spring. So they do exert some forces on each other, but these forces are weak, and there are only two of them. Okay? So we are going to apply F net equals mass times acceleration. Actually, we're going to do F net equals dp dt. We are going to try to apply that to the whole system. We only have experience in applying F net equals dp dt to one particular object or one system, but we are going to now try to apply it to a collection of particles. Right? So essentially, all that we need to do is just apply F net equals dp dt to each particle, right, and just get a set of equations. So let's see. Let's call this particle number 1. And let's call this particle number 2, right? What are the forces acting on particle number 1? Well, there is one external force, which is the force of gravity, let's say. And that would be, let's just draw that with like this. So let's call this F1 external, right? There is one other force acting on particle number 1, which is the force that's coming from particle number 2, right? And so that would be kind of in this direction. So let's call this 1, 2. F1, 2 just means force on 1 due to particle 2. So F1, 2 is just notation. It means force on particle 1 due to particle 2. Okay. And so that's all the forces that are acting on particle number 1, right? So it would be, so the Newton's second law applied to particle number 1 would be F1 external plus F1 2 is equal to dP1 dt. So that's the second law applied to particle 1. Applied to particle number 1. All right, let's do the same thing for particle number 2. So for particle number 2, there are again two forces acting on it. So there is F2 external, the external force on F2, which in this case is gravity. And then there is another force that's coming from particle 1, right? So that's going to be F21 in our notation. And I should really put vector signs on all of these. Okay. So Newton's second law applied to particle number 2 is very similar. F2 external plus F21 is equal to dP2 dt. And this is the same thing applied to particle number 2. So we have two equations which we got by applying Newton's second law to these two particles. Now let's just add up these equations and see what we get. So if we add them up, we'll get F1 external plus F2 external plus F12 plus F21. Can you tell me what's the result of adding F12 plus F21? Clearly the answer is 0, because F12 and F21 have to be equal and opposite. They are equal and opposite forces, right? And so by Newton's third law, they have, I mean, these two forces are an action-reaction pair is what I mean. So they have to be equal and opposite. And so F12 plus F21 would be equal to 0, because they're equal and opposite forces. So this is all that you're left with on the left side. And on the right side, you have ddt. If you just add up the two derivatives, you have ddt of P1 plus P2. This is the result that we are getting for our very simple two-particle system. Can we generalize this if you had if you have a very, very large number of particles? How would this result change if you have a very large number of particles? Well, you can probably see that you would get the same answer. You would get net external force summation Fi external so that's just F1 external plus F2 external and so on, is going to be equal to ddt of P1 plus P2 plus P3, P1 plus P2 plus P3 and so on. That's what would happen for n particles. Hopefully the extrapolation from 2 particles to n particles is clear. Everything would be the same. All the internal forces like F13 and F31 would cancel out, and F25 and F52 would cancel out. So all of the internal forces would cancel out according to Newton's second law and Newton's third law. And so you would get the result, which is on the PowerPoint slide. net external force is equal to the rate of change of the total momentum of the system. So net external force, so I'm going to write that as F external, and I'm just going to put this summation sign to indicate that the net external force on the system is equal to the rate of change of the total momentum of the system, and capital P is summation Pi, and that's the total momentum of the system. So instead of writing summation Pi 1 to n, I'm just calling that capital P. This is Newton's second law applied to a system of particles. Applied to a system of particles. All right. There is a very important fact that follows immediately from this result, right? What would happen if the net external force on a system vanishes? So suppose there is no external force on a system, or there are external forces, but they all cancel each other out. So if the net external force on a system is zero, right? I'm writing 0 with an arrow on top. That's the null vector. That's the equivalent of 0 in the vector world. So if the net external force on a system is 0, then dp dt is equal to 0, right? So what does that mean? Think back to your high school calculus. If the derivative of a quantity is 0, then what can you say about that quantity? It's constant. If the derivative with respect to time measures what is the rate at which it's changing, right? So if the derivative is 0, that means it's constant. That means the total momentum of the system cannot change. Or the total momentum of the system is conserved. That's a better way of saying it. And this is called the principle of conservation of momentum. This is a very, very important result. In fact, this is a fundamental law of the universe. So in chapter 6 and 7, we've talked about the conservation of energy. That's one of the fundamental laws of the universe, that energy is always accounted for. Here is one more fundamental law of the universe. Momentum is always accounted for. Momentum, if the total momentum of a system is always conserved if the net external force on the system is equal to 0. So if the so this is the law of conservation of momentum. Okay, so I'm going to end this video over here. In the next video, we are going to look at consequences or applications of conservation of momentum.